In this section of the PPST, we will look at numerical reasoning, including making generalizations, checking to determine whether statements are valid, or using if-then logic. So one way we can determine whether a statement is valid is to either use inductive reasoning or deductive reasoning. Inductive reasoning involves checking several examples in an attempt to determine whether a given statement is always true. We would have to know that there are infinite number of examples that we could try to attempt to determine the validity. Therefore, mathematicians often rely on deductive reasoning via proof or mathematical definition to draw some conclusions or the validity of statements. Again, checking several examples does not always lead to the correct solution. So let's look at an if-then logical connectors. A conditional statement is one that can be put in the form if A, then B, where A is called our hypothesis and B is called our conclusion. These if-then statements are used in deductive reasoning. For example, the statement if a number is divisible by 2, then that number must be even. We must remember that our whole numbers are the set of positive numbers including 0. And our if-then statement first has our hypothesis that says if a whole number is divisible by 2, that means our whole number can be divided evenly into 2. We want to know if that means our number is even. Well, if we look at our set of whole numbers, we are going to see that those numbers that are divisible by 2 are those even numbers. This is actually the definition for an even number. Therefore, this statement is always true, which means, inductively, if we selected any whole number that was divisible by 2, we would see that it would be an even number. A counterexample is just one example that shows a numerical statement to be false or invalid. For example, we could look at the statement, if the whole number is prime, then it is even. If we recall, prime numbers are numbers that have exactly 2 factors, one in itself. Our set of prime numbers are 2, 3, 5, 7, 11, 13, and so on. Each one of our numbers that is prime has only 2 distinct factors, one in itself. For example, the factors of 2 are 1 and 2. Factors of 3 are 1 and 3. We can see by a list of prime numbers that if our whole number of primes, then it is odd. This is false, since the whole number 2 is prime, but it's not odd. Therefore, 2 is going to serve as a counterexample. We would know that it only takes one counterexample to show that a generalization is false, but it takes an infinite number of examples to show that a statement is valid.